When they ask for a rate law or a rate expression, it's what we're used to. It's that whole rate equals rate constant, K, times the concentration, everything raised to the right exponent and orders. So far, we've seen a couple ways in which we can determine the rate or the rate law. Usually, though, we are given data, and within that data table, we have multiple trials. And in those trials, they're changing the initial concentration of the reactants, and they're monitoring and measuring the rate of reaction. And then you guys choose the table logic or the mathy way, and that's how you're determining the order of your reactants. That method only works when you're given the multiple trials with the different concentrations to begin with and the different resulting rates. But what happens when they only give you data for one trial and they give you multiple concentrations for that reactant and multiple times? So we can't use table logic or a mathy way to solve the problems if we're given that type of experimental data. Okay, the mathy way, the table logic, that's when you have multiple experiments, multiple starting concentrations, and multiple rates. When they give you concentration and time data, that's when we're going to go a different route. And the type of data given to you just depends on the experiment that they're running and the equipment and the reaction that we're doing. Sometimes we prefer the way we learned last week with a differential. Other times we're going to have to go this way. So we're going to use integrated rate laws when given concentration and time data. Use this method when you're given concentration and time data, and you're going to see what that looks like in just a moment. But before we actually look at some data, I gotta tell you, okay, what we do with that data. So to figure out the orders of our reactants, we end up taking that data and we end up graphing it. And we make 3 graphs, okay, and we look at those graphs and we know which order it is based upon the shape of the curve. Straight lines indicate a constant slope, which is going to be our rate constant. Okay, so this is going to sound really weird and it's going to look weird and you're like, what the heck does it mean? But trust me, it will make sense in just a little bit. So on my paper, I'm going to make 3 columns, and those are going to represent our orders. Okay, so we're going to take a look at what 0 order looks like, first order, and then second order. For each one of them, we're going to sketch a graph. Okay, and we're going to label the axes. On all 3, we're going to put time. Okay, whatever the experimenter is measuring, it could be seconds, it could be minutes, days, years, whatever unit of time. Now, these graphs differ by what we put on the y-axis. For the 0th order graph, we're going to plot square brackets, and we're just going to use the letter A now, and that letter A is the formula for the reactant. Okay, A is just a generic thing that we're writing. So we're going to plot concentration of the reactant on the y-axis and then time on the x-axis. So we would call this, in our formatting of titles, concentration versus time, right? Y versus X. And if the reactant is 0th order, which means its concentration does not affect the rate, you're going to get a straight line, a linear line, with a negative slope. And because the slope is constant, the slope represents K, your rate constant. So that baby K is equal to the absolute value of the slope. For the first order, we're going to plot natural log of the concentration of A, your reactant, versus time. If this graph produces a straight line in that manner, we know that it is first order. And since the slope is constant, the slope represents K, our rate constant. So baby K equals the absolute value of the slope. And K is always a positive number. And then finally, for second order, we're going to plot 1 over the concentration of A. If the reactant is second order, then this graph of the reciprocal concentration is going to produce a straight line with a positive slope. Since the slope is constant, the slope represents K, our rate constant. Okay, so when we're given that time and that concentration data, we plot these 3 graphs. Only one of them is going to produce the straight line. You go to that straight line, you read the y-axis, and you say, oh, because it's the reciprocal, oh, it's second order. Oh, because it's natural log, it's first order. Or because it's just concentration, I know it's 0th order. Now, these lines have equations to them. What's the generic equation of a line that you learn in algebra? Y equals... Yeah, that's right. Y equals mx plus b. Y'all got it. So that's exactly what we're going to do here. I'm going to write out y equals mx plus b. That's the equation of our line. And so I'm going to, instead of writing y, I'm going to write the variable that we have plotted on the y-axis for our 0th order graph. Since I have A plotted, I'm going to substitute A instead of Y. M is your slope, right? And we just said the slope is K. So we're going to replace the letter M with K, your rate constant. But because it's a negative slope, I do have to put a negative sign there. For X, we have time on the X-axis. So we're going to put a T for time. And then B, that's your Y-intercept. Or in other words, when the X value equals 0. And so it's going to be the concentration of A at time 0. This format, Y equals mx plus b, that's your integrated rate law. This is what we use when we're given time and they want us to calculate the concentration of the reactant at that time. Or they give us, hey, the concentration of the reactant is 5 molar. What time is it? Well, then you would plug in your concentration and then you would solve for time. So this is your integrated rate law. This is what we use when we have time and concentration in the same question. You're either going to be given the time and asked to solve for concentration, or vice versa. You'll be given the concentration and asked to solve for time. Okay, that's the one you're going to use if we determine its 0th order. Now, let's move over to the first order. We're going to do the same thing. Let's write out the y equals mx plus b format. Same thing. It was just we have a different y. It's natural log. So it's going to be ln concentration of A is equal to negative kt plus the natural log of A at time 0. That's your integrated rate law for first order reactants. Well, I should probably add the little t's here. On the y side, sorry for backtracking, for the y for natural log of square brackets of A, you can put a sub t because we're going to be examining it at a certain amount of time. That little t just means it's going to correspond to the time that we're plugging in. And I can do the same thing here for the zeros. Put a sub t there. It doesn't affect the calculation. It just helps you know that you should substitute in the concentration at that given time, t. All right, and then same thing here for the second order, 1 over the concentration of A at time t is equal to positive k times t plus 1 over the concentration of A at time 0. This is your integrated rate law for second order. They're all identical, guys. The only difference is what we're putting on the y-axis and making sure that you have negative k in all of these except for the positive slope. That has to be a positive k. Okay. Yep. All right. So we're going to do some practice with this, but before we get there, just want to make sure we have this in our notes as well. Half-life. You might recall from chemistry class or from earth science, especially environmental science. Half-life is the amount of time it takes for a substance to decay and lose half of its mass. So let's say you have 50 grams of a radioactive substance, and it takes 10 years for it to go from 50 grams down to 25, half its mass. The amount of time it takes for it to go from 50 grams to only 25 grams, that's called its half-life. And so in our example would be those 10 years. It takes 10 years for it to decay to half. And so in our AP chemistry class, when we're asked about half-life, we're dealing with first order. If you get a half-life problem, automatically we know it is a first order reactant. And that's because first order half-lives are constant. And that at this level, that's the only one that we deal with. When you guys go on to do more advanced chemistry, you'll learn about all the other ones. But for this class, we only concern ourselves with half-lives for first order reactants. So I'm just going to continue underneath the first order column. We only care about for half-life. Oh, not highlighter. Half-life for first order. Okay, so half-life is abbreviated as T1 half. And this is constant for first order. This is the only half-life we have to concern ourselves with in this class. The formula for half-life. Half-life is equal to the natural log of 2 divided by K, the rate constant. And if you were to actually calculate the natural log of 2, natural log of 2 is equal to 0.693. That's going to be over K. All right, so this one that I'm boxing here in red, this is on your formula sheet or your equation sheet from the AP exam. The one here that I'm going to highlight in blue, it's the same thing. For me, I have a better, easier time remembering natural log of 2 instead of 0.693, but it all means the same thing. Natural log of 2 is just an easier thing for me personally to remember than a decimal of 0.693. So when I'm doing problems and I don't have my formula sheet in front of me, I just think natural log of 2. Okay. But know that this equation in red is on your formula sheet. You know what else is on your formula sheet? The integrated rate laws. The y equals mx plus b. Those are also on your formula sheet. Okay, so do you have to memorize them? Kind of yes and kind of no. They're on your formula sheet, but as we know, the more we know here, okay, the better off we are, the faster we can move through tests, exams, quizzes, etc. So you can always access the formula sheet. You know, you have access to that in Schoology if you're interested in looking and seeing what is actually on there. So how does this half-life formula work? Easy. If they ask you for half-life, you plug in K and you solve. That's it. Or vice versa, they could give you the half-life, you plug it in, and you solve for K. Okay, so you'll be given the information for one of those, and you're going to be asked to solve for the other one.